Okay, well, today we start a new topic. I passed this handout out last class entitled Nested Experiment. So hopefully you got that with you today, and you can take that out as we take a look at this. Okay. So as it says here, we've got an experiment with two factors called A and B for short, and something different is going on with these two factors. So let me draw a little picture here that might help. The little factor is A. And the column factor is B. Say like that. So what I'm visualizing here is the kind of experiment we've talked about before. I have some number of observations per cell. Say I draw three observations per cell. And that's arbitrary. I could have any number of observations per cell in this picture. But anyway, in this kind of situation, we say the two factors are crossed in that each level of factor A is matched up with each level of factor B. So A equal 1 is matched up with B equal 1 and B equal 2. A equal 2 is matched up with B equal 1 and B equal 2, and so forth down the line. So if we have an experiment like this, which is the type we have been talking about, we say the two factors are crossed. Now, what's this new idea about nesting? Well, as it says here, let's take a look at this example 1. So factor A is a fungicide having 5 levels. B is a tree, and we have 10 different trees in our experiment. So if I try to look at this situation as it stands there, I would be seeing factor A has 5 levels, like that. And in factor B, there are 10 trees. So like that. So I have this array which is 5 by 10, 50 cells in all in this array. Now, these two factors in this experiment are not crossed because each level of factor A does not operate with each level of factor B. That would say that each level of factor A, the fungicides, has to be applied to each of the trees. And that's not a practical thing to do. Each tree is going to get one and only one fungicide. So that's what's going on here. So I've laid out a table here that might express that approach. So we have spray 1, 2, 3, 4, 5, and then for spray 1, there's 2 trees called 1, 2. For spray 2, there's 2 trees. Now notice again, I didn't call them 1 and 2. I called them 3 and 4 because they're different trees than the first 2. Then when I come to spray 3, I call the trees 5 and 6 because they're still different trees than the earlier ones. So instead of calling these 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, which we might have done before, that doesn't make any sense in this context because there's 10 trees as they're used here. 1, fungicide per tree. So in this language, we say that tree is nested in spray. Here's a second example of a similar nature. Factor A is one of 5 cities. Factor B is a school chosen in these cities, 2 per city. So in each school, 3rd grade students are tested on geography. Factors A and B are not crossed. Factor B is nested in factor A. So the idea would be that we're looking at a city, city 1. There's going to be 2 schools, 2 3rd grade classes, I guess, in that city that will be selected for the experiment. And then when we move to city 2, there are 2 3rd grade classes there used in the experiment. And the point is that these classes are different from one to the other. So we say that the factor B, the classes, are nested in factor A, and maybe using the word nested in this sort of typical English language way makes sense. The schools are inside the cities here in this example. So here's a picture of that scenario. There's the 5 cities. Here's the 10 schools, 2 per city. And notice I labeled them 1 through 10 rather than 1, 2, 1, 2, 1, 2, 1, 2, which we might have done in another crossed context. So I labeled them 1 to 10 to kind of emphasize that these schools are unique as far as which city they're going with. And then in each class, apparently, I'm getting data on some students. I drew 3 dashes here. Maybe that's indicating there's 3 students per class, but probably, practically speaking, there would be 20 or 25 or more students in each class. So those numbers would be higher than 3. So the overall question is, on this geography test business that we're talking about, is there any difference between the cities? Or are they essentially equal? Or are there any differences between the schools? So let's look here at the bottom of a model for a nested experiment. So we're going to talk about Yijk, where I is the index for factor A, J is the index for factor B, and K is a replication index through the replications in a cell. So that's the same notation that we've used before. No change going on yet. It looks a little different to your eye than earlier models. We have Yijk is mu, an overall mean, plus alpha I, that's an A effect. And then we have a beta J, but we don't have beta J like we might have written before. Notice the new notation that's going on here, beta J parenthesis I. And this parenthesis business is kind of clumsy, really, but it's classical statistical notation, I guess. So our book uses it. I'm using it here in these notes, and it's a little awkward, but this is what statisticians have come up with. So beta J parenthesis I means the effect of, what should I say, the effect of vector B being at level J within A equals I. So if I look back on the previous page, for example, I could say something like this. In the one about the cities, I could say A is the city, 1 through 5. So B is the school. So if I wanted to talk about B3, for example, there's B3, but the third school is nested in the second city. So somehow I've got to indicate that in the notation. The third school is nested in the second city. And what's the effect of that? Well, that's what this notation is trying to express. We have beta 3 paren, what was the number? I forgot, 2 maybe. So the effect of the third level of B, which is in the, whatever it was, the ith level of factor A. So anyway, we have this new notation here, which is supposed to help us out as we go along. We'll see what you think of that. The terms of the model are fairly standard. The errors at the end on the right are assumed independent normal 0 sigma squared. And the other pieces in this model, this is a fixed effects model, so they're constants. So there are some side conditions on these constants, which are kind of like the usual ones we've seen before. The sum of the alpha i's is 0. The sum on j of the beta j's is 0 for each I. And so we've seen those kind of side conditions before on the parameters in our model. And that's what we would have if the two factors are each fixed effects. In the case that both factors are random effects, then we change the assumptions and say these terms follow normal distributions, like that. And in the third case is a mixed model. Here we have A is fixed, B is random. So we have this side condition on the parameter for factor A. Now, as far as the randomness goes, with factor B, we assume these beta parameters are independent normals. I should say here, this is an unrestricted model. Remember when we ran across mixed models for the first time in an earlier handout, we had two cases. We called one case the restricted, the other case the unrestricted. And with the restricted model, we had various summations that the random variables had to satisfy. And so I didn't make too big of a deal about it at the time. So the issue is coming up here again as to whether in writing down the distribution for the betas, basically, we should put in some kind of summation constraints like we did before in what we call the restricted model. But we're not doing that here, notice. So anyway, those are the terms in the model, and we have three possible models depending upon fixed, random, or mixed situation. Now we have sums of squares, sum of squares t for total, sum of squares e for error, sum of squares a for factor A are exactly the same as before. We have a new one that comes up, namely here. And if you look at the definition of this sum of squares, it's got the mean in the ij cell, difference to the row mean, and then that difference is squared and then added up over all cells. So that's sum of squares B nested in A. For some notation, there's a notation for that sum of the alpha I squares, and there's some notation for that sum of the beta J squares. And so we start to summarize the information we have in this partial and normal table. So we have sources of variation, A, B nested in A, and error. Sums of squares A, B nested in A, and error. Degrees of freedom are those. And let's see, mean squares are obvious. Divide the degrees of freedom into the sum of squares. And now we have expected mean squares in the case of a fixed model. And here's the results. You notice that if I wanted to test about factor A, I would use the error mean square for the denominator. If I wanted to test about B nested in A, I would again use the error in the denominator. In the case we have both factors random, things change a little bit. Here's the expected mean square, and you notice that if I wanted to test A, the proper denominator is this B nested in A. It has the right expected value to do the job. So there's a change in the F-test on A, and then for testing B, again, the error is the proper denominator, so that's no change. And then finally, in the case of the mixed model, we have these expected mean squares, and when we look for denominators, you can see, well, to test A, you've got to use B within A, and to test B, you've got to use the error. So again, by inspecting these expected mean squares in the three cases, you can deduce the proper F ratios to use in testing the hypotheses. You might notice when the factor is fixed, the notation here uses the phi parameters. And then over here again as well, as is appropriate with a fixed effect factor. If you have a random effects, then there is no such phi parameter, but there is a variance. And so in the case when the factor is random, we have these sigma squares that come up in the formula, and that's appropriate for a random factor. So that's subtle, I think, but it does have an import as far as what's being expressed here with these equations. So the last line at the bottom of this page says, the variance of an observation is comprised of those three components. This is in the random effects case, where both A and B are random. And it says on the next page, the components of this variance can be estimated by considering the expected mean square column. Well, what do I mean by that? So both factors are random. We're in this case right here, and I want to know how should I estimate sigma squared B, and sigma squared A. I look at these results here, and I say sigma squared is estimated by mean square error. No doubt there. But if I want to estimate sigma squared B, I have to look at this middle line here, and so I have to subtract off something that estimates this sigma squared to get rid of that. So I'm going to subtract off a mean square error, and then I've got that in there that I have to still divide through by to get a mean estimate of sigma squared b. So we talked about doing that in an earlier example. Same thing is coming up here. So by looking at these results for expected mean squares, you can deduce estimates for sigma squared b, and sigma squared a. Now to confuse you a little bit, it says let's look at the fixed effects model. So in the fixed effects model, there's our model again for yijk, y bar ij dot would be the average of those on k, and the only thing that gets averaged is right in there. So we write e bar ij dot, and then we ask, well, what kind of distribution does this thing have? The first three pieces are just constants, so they will be in the mean. And the only thing that's random in this equation is the rightmost piece, the e bar, and that's a sample mean, and so it's going to have variance a sigma squared over n for a variance. So anyway, overall, this y bar ij dot is normal with that mean and that variance. Now if we go up one notch further and we look at y bar I dot dot, so now we're adding up on both j and k. When we add on j, we're going to get these adding up to 0 because of the side condition. So the betas drop out. And so notice it's not here. We have alpha I, nothing about beta because that sum is 0. And then we get an e bar I dot dot. What kind of distribution does this have? Again, it's like a one-step, write it down. It's normal with mean u plus alpha I, and variance sigma squared over nb. NB is the number of observations that are in this average. So then we go on and say, well, sometimes we want to look at this difference. Y bar ij dot minus y bar ij prime dot. So this is saying take two means that are on the same row, but different columns. They're in the same row, but different columns. Well, substitute in what we have above here, and you get this difference, and then plus this difference with the E bars. And so what kind of distribution does this have? Well, the mean is this constant in front, namely that, and then the difference of the E bars has a variance equal to 2 sigma squared over n in the usual way. So this kind of a result we might want to use if we wanted to make an inference about this parameter. Beta j I minus beta j prime I. So fix a equals I. And then look at two different j values and the difference between them. And so how do we make an inference about that kind of a quantity? Well, the estimate would be over here. And we can build a confidence interval around that estimate in the usual way. So I don't display that here. Then a related one is the last line here. Y bar I dot dot minus y bar I prime dot dot. So two different i's, I and I prime. So if we substitute in what we have, we get the difference of the two alphas and then the difference of the two e bars like that. Well, the difference of the two alphas is just a constant, so that carries over into the mean here. And then the difference of the e bars is normal with mean 0 and variance, here it is, 2 sigma squared over nb. So this line would be useful if we wanted to make an inference about this kind of a parameter here. We wanted to make an inference about the difference between two alpha parameters. This line would be the line we would use. Now, all this stuff in this layout, notice, is again for the fixed effects model. It doesn't even make any sense for the random effects model.
So same column, different rows?
Where are you looking?
The very last difference there. Y bar I dot dot minus Y bar
I is a
prime.
row, I prime is a row. Two different rows. Okay, let's look at another example here. So this talks about surface finish of metal parts. We have 4 machines. So here they are, machine 1, 2, 3, and 4. Each machine was run by 3 operators, and 2 specimens were collected from each. So machine 1 is run by 3 operators, and we get 2 observations from operator 1. We get 2 observations from operator 2, and we get again 2 observations from operator 3. Machine 2 is run by 3 operators, and we get 2 observations in each case again. And finally, machine 3 is run by 3 operators, and machine 4 is finally run by 3 different operators. And so the data might lay out something like this. So to describe what's going on in this experiment, we'd say, well, machine is a fixed effects. We have just 4 machines, nothing more. Operator is a random effect. We have lots of potential operators, employees in the company, and so we say operator is a random effect. Now, it goes on to say operator is nested in machine. Now, look at the situation and see that you can decide that. There are 12 operators in this experiment, and it looks like there's 3 because of the way I use the numbering here, right? I labeled operator 1, 2, 3, then operator 1, 2, 3, then operator 1, 2, 3, and that's done. I didn't make any mistake in doing that, but it's somewhat misleading because it seems to imply that operator 1 here is the same as operator 1 here. And that's the same as operator 1 here and operator 1 here, and that's not true. Those different operator 1s are 4 different operators. So we say the operators are nested in the machines in this experiment. So how do I analyze the data? Well, I'm going to show you some steps in Minitab here. Let's see. I should have redid this because this is a little confusing. I typed in the numbers like right there, just because they were easy to see by my eye. So that's going to take 2 rows and 12 columns. There they are in the Minitab spreadsheet. Okay. So I copied column 1 through column 12, and I put it in matrix M1. So M1 is a matrix with 2 rows and 12 columns. Okay. Then I transposed M1 and put it in M2. So imagine M1, transpose it. Now it has 2 columns and 12 rows. So that's M2. Then copy M2 into C13 and C14. Let's see, what am I going to get when I do that? M2 has two columns, so I'm going to copy those two columns into these C13 and C14. So C13 should contain as a column those numbers there. And C14 should contain as a column those numbers in the second row there. Then I'm going to stack C13 on top of C14 and store the answer in C15. So that's going to basically take these numbers that are in that row and put them on top of the numbers that are in this row, which is going to give me finally a column which contains 12 and 12 and 24 numbers in it, and that'll be in C15. I was trying to avoid typing in all the numbers. I think I made it more complicated than if I would have just typed in all the numbers directly. But at this point anyway, column C15 has the data there in one column. The first 12 and then the next 12 are in the second row there. So that's column C15. Now I'm going to set up a new column C16, which is defined this way. And the way this works is it's going to take 8 ones. I think I'm doing this right. 8 ones and 8 twos and 8 threes. This is going to give me a 1, 2, 3. 1, 2, 3. And then that's repeated up to 8 times. 1, 2, 3. Okay, so that's C16. Now I lastly define C17 to be this way. 1, 2, 3, 4, repeated 3 times. 1, 2, 3, 4, repeated 3 times. Now here, the repeating count is on the right, whereas above it was on the left. And it does things differently. If I say 1, 2, 3, 4, repeat that 3 times, it does a 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4. It does that. And that's what I want for machine, because these 3 have machine 1. And then the next 3 numbers have machine 2. So I want 2's. And the next 3 numbers have machine 3. So I want 3's. And the last 3 numbers are for machine 4. So I want 4's. And then I've done that for the data that's in this row. And then I've got the data that's in this second row yet tagging along. So I've got to repeat that a second time. Now what I should have done after this clumsiness here that I've shown you on this handout is I should have printed out the columns in Minitab so you could see what I've created. Okay, so anyway, there I'm setting up the data. And basically I want I'm looking at the symbols here. So I have Y, which is the data. There should be 24 numbers in this column. Then I have machine, which is going to be the 1, 2, 3, 1, 2, 3. I've given that the name machine, so that's okay. But now here I'm stuck because I've got nope, that can't be machine. That's what I would get if I had operator. If I want machine, it has to be 1, 1, 1, 2, 2, 2, 3, 3, 3, then 4, 4, 4. And then that's got to repeat itself again for the second row of data. So okay, there's my, what should I call it? There's my spreadsheet information. And I should redo this to give you a better view of this spreadsheet. So anyway, you have to trace this all out yourself. But I finally come down to here, the GLM command. So Y, the response, is machine plus C16, notice the parentheses, C17. So the parentheses is used in Minitab as a syntax for nesting. So column 16 is nested in column 17. In this particular problem, operator is 16, and it's nested in 17, which is a machine. So 16 is the operator, 17 is the machine. But anyway, notice the parentheses there. That's interpreted by Minitab as nesting. So you're telling Minitab operator is nested in machine. Now, I've done subcommands. I've indicated that operator is a random variable. Okay. Brief 2 isn't very helpful. I want to see the expected mean squares. And now what I'm trying to ask for is I'd like to get pairwise Bonferroni information. It says no test, so maybe I'm not asking for tests. Maybe I'm asking for confidence intervals, but I want pairwise Bonferroni confidence intervals on the sheet. Now, these aren't lines that I type. These are checkoff boxes in Minitab Mini. So I just checked off those things, and this is what it produced. So anyway, let's see what Minitab did. So it tells me machine has 4 levels, operator has 12 levels. And that's kind of clever to notice because it's operator parenthesis machine. Operator nested in machine has 12 levels. So it counted that there's 12 different operators in this experiment. Right? And here's the numbers used in that column, but there's 12 different operators in this experiment. Let's sort of pick that up in what we said. So then it produced this analysis of variance table nicely for us, which has an F-test for machine, it has an F-test for an operator. And let's see, this is a mixed model. A is fixed, B is random, right? So if we look at our mixed model results, back on page 2, this is what we should be looking at. here. So the proper denominator for testing B within A is the error. The proper denominator for testing A is the B within A. So let's see if the numbers kind of match up over here. So for this bottom F, we should be taking the quotient of these two mean squares right here, 354 over 85. And that comes out to be about 4. So it's doing that right, I think. Now the F of 3.1 should be the top mean square divided by the second mean square. So 1098 divided by 354 should be about 3, which is what it's got here. So anyway, a small kind of hand check shows me that the program was using the right F ratios for these F statistics. It's got degrees of freedom to use over here, so it runs the usual F tests, and here's the p-values. The first is not significant, the second one is. Now here's a layout for the expected mean squares, and they should match up with the formulas that we had back on page 2. On page 2 we had these formulas over here. The n is the number of observations per cell, which is 2 in this example. So the n is 2, and then nb I didn't think it did anything with that. It just says Q1. Q1 is sort of loose notation for a bunch of stuff involving the machine parameter. But anyway, there's the 2.00, that's from the little n. So those are matching our textbook formulas. Then it tells us which error terms did it use for the tests, and so we can check it out, and it's visible up there as well. Then if we want to estimate the variance components using adjusted sums of squares, we have operator is random, and error is random. The other variable, machine, is not random. So machine is not in here. There's no variance component due to machine. That's a fixed factor. So anyway, it gives us some numbers here, and we're okay on that. Then there's this warning. No multiple comparisons were calculated for the following terms which contain or interact with random factors, machine. You remember in the commands I had asked for, what was it again? Bonferroni, pairwise, confidence intervals, basically, on the variable machine. And so it's telling me it can't do this. It can't do this because we have interactions with the random factors. I'm not sure quite what that means, but anyway, it just says I can't do that for you. So I asked for some descriptive statistics. Describe C15, break it down by C17. 17 is the machine. So here's the 4 machines. Here's the means and standard deviations and so forth. Okay. So if you stop and stand back from this mini-tab exposure that you see, what am I doing here? I've got a balanced nested data set. And I'm running Minitab to do the two tested hypotheses. And that's all that I've done here. I'm curious about this descriptive statistics information that pops up here at the end that I asked for. I have the 4 machines. Here's the means for those 4 machines. And then there's other standard deviations and so forth there as well. So why can't I use this information to make pairwise comparisons between the machines? The program wouldn't do it. Why wouldn't it do it? Well, let's look back a little bit. When we were writing down the model, I said back on page 2, there's the model equation. And we had possibilities of both factors fixed, both factors random, or the mixed model situation. And then we said at the bottom here, in the random effects model, this is the variance of the y. We don't have any mean of the y to be interested in. There's no mean of the y to be interested in the random effects model. So there's only these variances that are of interest. And then it goes on to say, well, you can estimate those by considering the expected mean square column. All right. So then the handout goes on and says, in the fixed effects model, these are a bunch of equations. Okay. And it gives the distribution of these kind of differences of means. Okay. Now, these results here are applying to the fixed effects model, right? So if I wanted to say, what's the, I don't have it on this page. I guess what I'm trying to say in an awkward fashion here is that I'd like to know what the results are in the mixed model as well. And I don't have them here for you, right? So it's something we'd have to kind of write down and try to explore. What would be the corresponding results in the mixed model? So when I finally get down here on page 4 to this layout of the 4 means on machines, I could say I could be interested in these differences, but what kind of distribution would I be dealing with? I'd have to worry about a plus or minus a standard error. What would be the formula for that standard error? It's not the one that was earlier in this handout because that was for the fixed effects model. So it's a new one that we have to develop. I haven't done it here, so I guess I'm telling you, just kind of skip over it, but notice that it's kind of a hole in the story. It's not impossible, it's possible to do it, but there's a hole in the story there. So summarizing then this Minitab example, what you should see here is that this is kind of easy stuff. We need to recognize that we have a nested situation. And we tell Minitab that's what's going on with this notation here of the parentheses. So once we've done that, Minitab is cued to say one of these variables is nested in the other one, and which way it goes is indicated by the notation there. And So Minitab just takes over and gives you an over table here on the top of page 4 with the F-tests that are there, and it's easy. No big deal. There's the results. All right. So, well, that's good. There's not a whole lot new as far as what test statistics are we calculating here in this nested model. Minitab takes care of it. So now I'm going to take up a harder problem, unbalanced two-factor nested models. We saw when we had two-factor ANOVA problems before, when we had unbalanced data, there were some problems in the F-tests. It didn't work quite right. So now we're going to run across unbalanced two-factor nested model. So here's the notation. I goes 1 to, what was it again here? A, for factor A. J goes 1 to BI, for factor B within the ith level of A. K goes 1 to Nij, for the replication within the ith level of A and the jth level of B. Ni dot is the number of observations in the ith level of A. So anyway, we have some notation for number of observations that we have. So here's our model equation again. That doesn't have anything to do with the sizes of the samples, so whether the samples are balanced or not is irrelevant there. Case 1, both factors are fixed. Case 2, both factors are random. Case 3, we have a mixed model situation. So the means are defined in an equal way, so are the sums of squares. Now here's something new that's happening here that we haven't encountered before. I'm defining a constant A1 to be that. And if you look at what's in here, it involves the sample sizes. It does not involve the data. So it only involves the sample sizes. Here's A2. And you look at what's in there, and again you say, well, that involves the sample sizes. It doesn't involve the data. And then here's another constant, B1. There it is. And again, it involves the sample sizes in various ways. So anyway, the formulas are a little messy to look at. But anyway, we can loosely say A1, A2, and B1 are constants dependent on the sample sizes. And why do we want those? Well, here's where it comes in. We don't have any change at all in this column here. So the expected mean square column is the same as we had before, and so the F-test will be the same. It's the same, if you've got unbalanced data, do it. Now, when we have a random model, both factors are random. Notice there are changes here. We have A1 and A2 and B1 appearing here. And so what would be proper F to F ratios to use in this case? Well, we have to juggle around a little bit with some pseudo F test, like we have done once or twice before, but because of those coefficients not matching up so nicely, we would have to worry about a pseudo F test, especially for factor A. Then when we come here to the mixed model situation, okay on B within A, so that one's got a natural denominator. But when we want to test factor A, there's no natural denominator in the list here, and so we have to build a pseudo F test statistic for testing about A. So in both of these last two columns, for testing A, we have to build pseudo F tests. For testing B within A, it's a direct denominator to use. So how do we do the pseudo F test? Well, here's some detail about it that comes up next. Why do I have that shadow there? Well, so it's going to talk about how do we build this pseudo F. We need a denominator. So we start with this mean square, it's just called. Theta, the moment theta is arbitrary. Mean square b within a plus 1 minus theta mean square here. So this is a linear combination of these two mean squares. Now we choose theta, so that the expected value of this is what we want. And what we want is that. So it's a couple steps of algebra. I didn't write them down here. On solving that algebra problem, that theta should be A1 over B1. So if you know what theta is, now you can calculate MS, this mean square. Now, this cobbled together mean square has some estimated degrees of freedom, which follows, quote, the old formula from Satterthwaite. Messy as it is, there it is, the estimated degrees of freedom for such a mean square. So I think it's typed correctly. So plug it in and use it. So to test A, use mean square A divided by this new created pseudo mean square. Degrees of freedom would be A minus 1 from this mean square, and then this thing, R1 as I call it, for the denominator mean square. So that's all a doable thing. Okay, so now in this handout, I want to have factor B nested in factor A. Factor A is fixed, factor B is random, and here's the data. So you see factor A has 2 levels, 1 and 2. Factor B has 2 levels when A is 1, and 3 levels when A is 2. So it's not balanced that way. And then in each cell, I have different number of observations. 3 observations in the first cell, 2 in the second, 4 in the next, and so forth. So we have quite a bit of unbalance in this data set here, but it's a nested situation. B is nested within A. Now, how can I get this to run? So in the Minitab menu, I go to the ANOVA choice, and one of the selections there is fully nested ANOVA. And that looked pretty good. So I tried it. And this is what it gave me. There's the command it's using, and here's the table with the mean squares. It's talking about variance components. It's talking about expected mean squares given by those. And you'll notice in this expected mean squares part that these coefficients here are not necessarily nice integers as they are in the other cases that we looked at. They're messier because this is like the A1 and the A2, and those are kind of messy expressions involving the different sample sizes. So whatever, there it is. The program did it for us. It says now you can see that there's a switch of font here, right? That means that now what follows isn't coming from Minitab, it's what I typed. So I should have emphasized that in a little better way. A direct F-test for B is possible from the ratio of those two mean squares. 51 something over 3 something is 14 with those degrees of freedom, and it's significant for sure. Now for factor A, we have to use a pseudo F-test. So here I'm trying to figure out the theta, and then the mean square, and then this new F. Significant in any way whatsoever. So after I had that output, I'm on the last page, page 8 of this handout now, it said, I have doubts about the above nested command. Let's try GLM. So then I tried GLM y equals a, b nested in a. Notice I'm using the nested syntax here to indicate to Minitab that factor b is nested in factor a. B is random, giving the expected mean squares, and so it produced this stuff. Well, here's the ANOVA table. Here's the expected mean squares. The error terms for the tests. And in this stuff right there, I just checked by hand that for this data set, A1 is 2.68, which agrees with that number there. B1 is 3, which agrees with this number here. And A1 over B1 is the quotient of those two, and it's 0.89 something. Why do I want that? Because of this down here. Because there's error terms for the tests using adjusted sums of squares. Source A, and then error degrees of freedom. Notice this isn't an integer, so it must be estimating degrees of freedom with the Satterthwaite formula. That is an integer, so now here's the denominator mean square, 0.892 plus 0.103. And the 0.89 is coming from there. And the 0.10 is 1 minus 0.89, so they're connected that way. Let's see. Now, what I can't remember doing is, did I check that that was the denominator that was used in the pseudo F test about A up here? And maybe I'll just have to turn it on your shoulders and say, check it out and see what you find. Because they should be connected together somehow. I wrote over there, correct. So somehow this is coming out correctly. And what this is leading me to say is that the previous minitab run, which was using the nested command, I don't think is correct. What can you do when your software gives you the wrong answers? And it doesn't tell you that it's the wrong answer, of course, right? So there's my dilemma. So I think this second way of doing things, using the GLM command that's important here, is the right way to do it. And I don't believe the nested command is the minitab, at least today. Well, if that's the case, you look at this and say, okay, if I have a nested data set, how am I going to analyze the data? You can say, put it in Minitab and do this. You're going to get a nice ANOVA table. If need be, you'll have to cobble together a pseudo F test. If it's unbalanced, especially, you'll have to do that. And but there's no real big deal. It's pretty much the same kind of ANOVA testing that you've encountered before. So that's all for the good. What if we had 4 factors? Factor 2 is nested in factor 1. Factor 3 was nested in factor 1. Factor 4 was nested in the cross between factors 1 and 2. This can blow up on us really, really fast. Okay, so we're looking at here in these handouts some of the first basic kind of situations. But in real experiments, they can get much, much more complicated than these examples that I'm showing you here. And well, we got to start somewhere. So we're starting with the simple examples here in these handouts, and we can go further as you desire. So let me know. All right, that's enough for today. Let me stop talking there, and we'll continue here next week talking about some nested things again. Okay.